So, nice. Okay, so it was going backwards and forward. No, did you do it, Michael?
I clicked on it.
Maybe it's not. Okay. Good. So here's the overview. So the usual thing, introduction. Then I will talk about the symmetries. I will briefly remind you about what the inverse seesaw mechanism is, and then I will put these ingredients together and discuss two scenarios which I call option 1 and option 2. And as you see in parentheses, I write out what's the main pheno, which I will focus on for each of these options. And in the end, I'll summarize. Please interrupt me anytime if you want. Also, the people on Zoom, feel free to. Now, the standard introduction. So, standard model works very well. We are all happy with that. However, not all things are understood, or we think not all things are answered. For example, we are still puzzled by the fact that there are 3 generations, although actually, as you heard many times, you just need essentially the first one to make up all the stuff which is around us. If you're not opting for doing, let's say, energy colliders, you will not see second and third generation likely. Then about the fermion masses, many things you could be puzzled about. Some people say the hierarchy, others say maybe the disparity between the neutral states, the neutrinos down here, and the charged states up there. You might be also puzzled about the fact that maybe the neutrinos, likely or not likely, have a different hierarchy. Maybe it's inverted. Maybe it's like the one as we know from the charged states. So that's another point which you keep an eye on and you say, okay, that looks weird. When you come to the other essential ingredient for fermions, it's not only masses, it's usually also mixing. You stare at the quark sector and you see essentially there's an identity matrix, which means hardly any mixing apart from the Cabibbo mixing, which is here with this 0.2. While for the leptons, which is encoded in the PMNS matrix, looks totally different. Essentially, the only small entry you have over here is theta 13, which reaches up to the size of the largest off-diagonal entry, which is 0.2 Cabibbo angle for the box. So it looks all very different. So maybe this tells you there are different mechanisms for generating the masses behind. There might be different structures, symmetries, organizing principles, whatever you like to call it, behind this here. And that's what we would like to address in this talk. So there's another point. Obviously, there are many other things. So BU, for example, Yanis is very much interested. Dark matter, Lorenzo last week was interested in. These are things I'm not going to touch up on here. Rather, what I would like to emphasize is in this context of flavor, if you go, and we like to do this very often, beyond the standard model, actually these theories usually have a very rich structure in flavor, if you wish. Because, for example, many processes which are highly forbidden, highly suppressed or forbidden, are kind of naturally there in extensions of the standard model. We will, for example, look at particular at cLFVs, and one prime example is the mu 2 gamma, which has now a limit of roughly 3.1 times 10 to the minus 13. And so if you think about classic extensions of standard model, which would be supersymmetric with low scale SUSY particles, this actually can be easily violated. So this usually gives a very strong constraint on BSR models. Then it's not only this one particular process, but it's very well known that all kinds of flavor processes also involve quarks, as well as potential new sources of CP violation, need to be well under control. Otherwise, you will get too much of it, of what actually we have already excluded experimentally. If you think about CP violation, a prime example is you think about the EDMs of the electron, for example. And then there's the last point, which is probably more like theory inspired, or it can also be experimentally inspired, is that what you would like in order maybe to have a guideline of what could be the right theory beyond the standard model is something. There's some possible correlations we could have at different types of signals. When we ever see a signal of these sort of processes, we look out for correlations to understand what is actually the right way to go beyond the standard model in one way or the other. Okay, that much about the introduction, the general stuff. Now let's come to the symmetries. So that's kind of very much inspired by saying gauge symmetries are very nice. They helped us a lot in understanding and in building the standard model. So let's try out a new type of symmetry. Now we throw any kind of symmetry on what is called the flavor space, so the space of 3 generations on the fermions. Here, just a little example. Imagine you have something which is just a permutation symmetry among the 3 generations of quarks. So what roughly is going to happen? This will constrain your Yukawa Lagrangian. It will constrain the Yukawa couplings you're allowed to write down, which means as consequence, it constrains the quark masses you can expect, as well as the mixing. Okay, so that's a very brief motivation. So now, if you accept that there is this kind of new symmetry, the next question you logically ask, what properties has such a symmetry? And here you see a long and very much familiar list to you. Namely, you can ask yourself whether a symmetry should be abelian, non-abelian, whether it should be continuous, discrete, local, global. Each symmetries you like more local symmetries than global ones, but maybe another type of symmetry is more global than local. Then obviously symmetries are usually broken. And then the question is in which way, at which scale, and so forth. So now here's my take on these choices here. I just emphasized 3 things. So I would like to have a non-abelian symmetry. I'd rather like to have it discrete, and I'd rather like to break to non-trivial. What's my motivation for it? So non-abelian, simply because I would like to have a reason why there are 3 generations. So I imagine packing the 3 generation in one irrep of the group, which means I need a non-abelian group. Then I'd like discrete groups, because just think about, for example, crystals that have discrete symmetries. You usually notice that they are preferred directions. So I like these preferred directions because along these I can break the symmetry, and with these I can connect eventually a prediction for lepton mixing, in our case concretely here. And lastly, I like to have non-trivial subgroups. I don't like to start with a big symmetry and then just say everywhere it's broken in a total arbitrary way and whatever. So simply because I would rather have a very predictive scenario. I try to make it as predictive as possible. And you will see how we do it. And that's my starting point. Okay, good. Then you might ask the next question, okay, be more concrete. What are the types of symmetries we are really talking about? Discrete symmetries. Yeah, the list is not that short. Usually many series, you see these indices, and many people worked on that as well. If you're interested a bit more in the literature, maybe start with these reviews down here. I will make my choice for today. My choice for today will be these delta 3n and delta 6n. I will give you a very short introduction so that you get a glimpse of why I choose them, why I like them, and why they're easy to handle. And I also would like to involve CP. As I told you, CP observables, one should keep an eye on if you go beyond the standard model. On the one side, on the other side, if you include CP also into the game, you might have the chance, and this I will show, if you think about leptons, to predict all the 3 CP phases you have, assuming that the neutrinos are Majorana particles and that the lightest neutrino mass is non-zero. Okay, good. So what are these delta 3n square, 6n square groups here? So what makes them nice, or why do I like them? They have three-dimensional errors. So we can explain why there are three dimensions. Good. If you want to have also one and two-dimensional ones, they're also. What makes them easy to handle? They are a series of groups. These are all subgroups of SU3. That's good. That's something we know very well. How do you typically describe such groups? So you take n times n matrices, so one-dimensional ones, two-dimensional ones, or three-dimensional ones, depending on the representation you like to describe. And you have three what we call generators, ACD. They have to fulfill certain relations, which you see down here. You can write every element of the group in this one, which is also nice. And in this way, you can make a group, and you can study essentially what kind of couplings are allowed and not. Okay? The delta 6 and square groups are similar. You just are forced to add another of these generators, another matrix if you want, which fulfills again a bunch of relations here, and then you can write all elements. So that's very easy, very basic. In principle, you don't really need to know more about these groups. And so that's my choice. Why I like it, I try to expose that because they have these three-dimensional Erbs, they are subgroups of SU3, so they're easy to handle. And in addition, they are series, which I can treat all in the same way. So I can study a large class of groups at the same time, which is also nice, instead of just picking one and do all over the same thing again. Let me now move on, because I said we also want to add CP as a further symmetry. So CV, you know very well. I would like to make a little step beyond what you probably usually do with CP. Namely, I would say, think about the fact that if you have more than one generation of a certain species, let it be scalars in this case. Okay, these phi's you imagine as scalars. The easiest thing to do CP is you say, like, I have my phi1, it goes to its own CP conjugate, which I call phi1 dagger, and has this. Now the space-time point is going to be XP. But this is not the most wished general CP you can write down. In principle, you can also just mix, if you want, these generations among each other. And this is what this matrix X Aj does. So this matrix has certain constraints. As you might very naively expect, this matrix should be unitary. It's going to be an n by n unitary matrix. You see I have an addition more strong constraint, namely that this is a symmetric matrix. This I actually like to have, because otherwise I would get constraints on the neutrino mass spectrum, which actually render it incompatible with experimental data. I can talk about this in more detail, but this I just say is a standard constraint which people use when they deal with such kind of scenarios applied to neutrinos. Okay, so if you want to have it mathematically, because you might now ask yourself, okay, which kind of X shall I choose? Assume I have this flavor symmetry, one of these, which I've shown before. So which kind of X shall I choose? Mathematically, just watch out what are the automorphisms of this flavor symmetry. That's very easy. Again, you can make up a list. And now you have everything at your disposal. You have the symmetries at your disposal, and you have the CP at your disposal. Now comes the next step. The next step would be, as we said, we are not going to, I am not going to break the symmetries in some arbitrary way, but I just like to break them to some residuals. And what's the purpose behind all that? So if now we imagine, again, we have the big symmetries to start with, and now we look at leptons. So now I'm telling you, assume that charged leptons know about some residue, which I call Ge. Neutrinos know about another residue, which I call G nu. So what actually is this corresponding to? The fact that these two groups should not be identical is corresponding to the fact that there is non-trivial mixing between the two sectors. So that there's misalignment, between the mass bases, if you wish, which actually gives you here the lepton mixing matrix. So what I have done in that sense, I have now rewritten lepton mixing in terms of residue symmetries. And since residue symmetries are not arbitrary, if I start with a given set of symmetries, I will not have an arbitrary outcome for lepton mixing, but I will essentially have some prediction.
If I understand this correctly, you're breaking GF on the left hand side to GE,
yeah,
with CP broken,
yeah,
and on the right hand side you're breaking GF down to Z2,
yeah,
and the
CP is still there.
conserved.
Exactly. What would happen if it wasn't there on, it was there on both sides? Obviously, you wouldn't break it at all, and I would get always trivial faces.
Right. And this breaking is explicit or what? So this is a discrete
for what I'm doing now, I don't need to specify it. I can give you examples where it's explicit. For example, if you think about extra dimensional models, you can have that it's broken explicitly at a certain brane.
Why is that explicit?
And this is explicit. 90% of people do it actually spontaneously. I don't care here. So that's the short answer. You're not, I mean, if you want to think about really a way of bringing it, so imagine that there are certain fields, which, I mean, most likely gauge singlets because you want to decouple the breaking of the electric symmetry from the wave symmetry, probably. Then imagine that there's a bunch of gauge singlets, and this usually can do the job. And there is a vast literature on it. People achieve this for concrete models, including these type of models. Yeah, thanks. Mm-hmm. Yeah, and
so would it be, I mean, okay, I don't know, you keep CP in the neutrino part.
Yeah.
Would it be possible to create the same model with just CP but conserved in the charged lepton part?
Yeah, so you can do that.
Energy?
If you do that, what happens there? You will not be able to have any prediction on the Majorana phases which come from the neutrinos. So you will be less predictive if you want, right? So why do I like to have CP over here? So look at that. So actually, you can also ask me why actually I use the 2 over here. The 2 over here I use because I want to have Majorana neutrinos. And the largest compatible symmetry with the Majorana nature is a Z2. Or it's a Z2 times Z2 or Z2 times Z2. Yeah, it depends on the number of generations of the Majorana neutrinos you have. Now, what I want to do here is kind of a compromise. Instead of beginning, people took Z2 times Z2. Then you totally fix mixing, but you can't say anything about Majorana phases because you have not entered, your CP has not entered into the game. Here I want to do a compromise. I keep one Z2, but I replace the other one with CP, which is a sort of Z2 because it's an involution. What is the Pheno impact, if you wish? Having just one Z2, I get this free angle here, as you see. Having the CP, I get on the plus side, I can fix the Majorana phases. That's the essential point. If you want, I can enter in more detail to that, but that should not be the main point here of the talk. So what actually can I do then? So now we kind of clarify this side. For the GE, I only say that my minimal choices is Z3. So why is that the case? Because I want to give 3 labels which are different to the 3 charge leptons, which just tells me there can be 3 different charge lepton masses. And no mixing coming from that side if I'm sitting the appropriate basis. So what's my goal here? Actually, I want to have some predictive result for the PMNS matrix, which depends only on this one 3-parameter theta. And I can't give you any prediction for the masses apart from that they have 3 parameters for me. Okay, that's the point here. Good. Now, coming back to the delta groups. Yes, you can do this funny study with the delta groups, okay? And the funny point is you can actually go through all possible choices of this GF you have, which is one of the delta groups, the GEs you have, and the possible GNUs, so the different Z2 symmetries which are in each of these delta groups. proves then the different CP symmetries you can use. But it comes out that you can categorize the results for the lepton mixing in 4 different cases, which we call. That's nice. I mean, you might have expected, because if you start with a lot of stuff, there might be more possibilities. They're just 4. Just let me give you one kind of some brief idea. But the easiest one is what is called case 1. So then you can write all the lepton mixing angles in terms of this one free parameter. You see now my predictions for 2 of the CP phases are boring because they're just trivial. And the third CP phase actually is related to exactly the choice of the CP symmetry which I make. So you can put it the other way around. If you are able to measure the CP phase for measuring neutrino stable beta decay, you can tell me in this context which is the CP symmetry that nature has chosen.
So what is n? Is it the size of the group that you're playing?
Yeah, n is the size of the group. Yeah, because it's always delta 3n square or delta 6n square. So
and s just counts the.
Is a label for the CP symmetry. Actually, it runs from 0 to n minus 1.
Yeah, that's what I expect. And theta L is
this free parameter.
It's a free parameter,
which we have seen before here. And depending on whether you can actually find the value of theta, which gives decent results for all the 3 lepton mixing angles, and depends on whether you are in agreement.
But if it's a free parameter, I can choose it to be whatever I like, right? I can in principle.
You fit it. You fit it.
You fit
it. It's now you say, like, is there any chance of that this stuff here is in agreement at 3 sigma level with what, for example, new fit tells me?
Yes.
Yeah, it is. You could get this is the minimum of your fit, one-dimensional fit, where this theta is 0.18 or something. Okay. If you find that boring, you can do something which is a little less boring. Here you would see something where the lepton mixing angles actually depend not only on this theta, which you now see on this vertical axis, but also on a parameter which is called u. And u actually is telling me, give me some information about the CP symmetry. There's also v, which is the complementary information because the 2 free parameters are s and t, but you can nicely rewrite it in this u and v. But only this part here is fixed by the desire to fit the lepton mixing angles. So, and in order to fit this stuff, the lepton mixing angles, which we know well, you have to sit on this arc. Mainly this arc is determined by theta 1, 3. And how this has been measured. And now what you can see here, there's some difference between normal and inverted ordering because the data is different. You see also there's a difference where you include the hint, which is maybe there for the CP phase delta, or you don't include it at the C sigma level, but just to give you an idea. Okay, so you find already some constraints in principle. This already constrains the combination, the choice of CP symmetry you have, which actually has a chance to fit the data level. Even though you have this free parameter, okay? It's not everything free. Good. Here are also some numbers, some concrete choices. If you want to think about some concrete n, for example, 14 would be 1, then you have this u, which is between 0, 1, and minus 1, okay? Good. So that was about the symmetries. Now, we have no urgent question about the symmetries. Let me just very briefly walk you through the inverse seesaw mechanism, which you all have seen many times. So what do you do for an inverse seesaw mechanism? You add 2 types of states. One you call n, the other one you call s. Actually, they're all gauge singlets, and with respect to the Standard model, you don't distinguish them, but imagine you had some left-right symmetric extension of the Standard model, then you would distinguish. What do you want? You want to write down 3 types of terms in your Lagrangian, these ones, 2 of Dirac type and 1, as you see, is Majorana. So if you assume that everyone comes in 3 generations, which I would like to do at the moment, you get a 9 by 9 matrix here. And now, a priori you would say, like, okay, this is going to be complicated. However, if you assume now that the parameter which breaks lepton number here, this is only the mu here, this mu s, is much smaller than the Wick scale. While typically this parameter here, which determines the scale of the new states, is the TV or so. It's usually larger than the weak scale. Then you can get an approximate formulation for the neutrino mass matrix, the light neutrino mass matrix of that one. And you see if the mu goes to 0, also light neutrino masses disappear. It has been known since 40-ish years, 35-ish, 40-ish, almost 40-ish years. Okay, and then you can ask me, okay, now we know what happens with the light states, what happens with the heavy guys, which we added, this N and S. Actually, they form what is called pseudo-Dirac pairs, because you have this hierarchy between this part here, this M and S being TV-ish, usually, and this mu S being something like a KV or so. If you diagonalize this structure here, you will roughly get 6 states, of which 2 of them always have nearly the same mass, plus opposite CP parity, so they form pseudo-Dirac pairs. That's the characteristics of the masses. Now you can ask, what about the mixing? The mixing now gets complicated because it's a 9x9 matrix. Actually, you're mostly interested in this upper part here, this U tilde, because that part is what naively diagonalizes the light neutrino mass matrix, which I've shown you. So this is your, so to say, quote-unquote PMNS matrix. And then you would have this other part, this V, which diagonalizes the heavy ones. But let's stick with the U tilde. So what's kind of new maybe for you for the new tilde is that this, as I said, is part of a 9x9 matrix. So actually it's not unitary. It's not what you would expect from a standard PMNS matrix. But you can usually parameterize this thing as a unitary matrix times some deviation. And this deviation is encoded here in this eta parameter, which you calculate once people tell you what the matrices MD and MNS. So it's actually evaluating the impact of the heavy states on the mixing of the light states. So how much this matrix is unitary. And this obviously is strongly bounded exponential. Good. Questions until here? Oh, that's so far so good. Then we would say we are now ready to start with the first scenario. So now we put all these things together. So we put the symmetries together, flavour and CP, and we put also the indices together. What does this mean? You tell me which kind of fields you have. So we are not only looking at leptons. So we have charged leptons, right-handed ones, we have the left-handed lepton doublets, and we have these new states here. So what's the story? Now we have to decide how they should transform under the symmetries which we would like to have. So let me start with the left-handed lepton doublets. I would like to have these being in this complex three-dimensional irreducible representation. Why do I like to have this? Because if it's this irreducible faithful complex representation, so important point actually is here mostly faithful. That's kind of, what does it mean faithful in let's say, poor people's words means kind of, it's reflecting all the structure of the group, okay? Not only from a subgroup of the group you're looking at, but the entire group. Which means if you start out with that, you will be able to explore all kinds of lepton mixing patterns which you could get from a certain symmetry. What I told you before. Good. Then you look to the right-hand side. I'm not very creative about right-handed charged leptons. I put them just in singles. Why would I like to do that? Because, as I told you, I'm just interested in saying that there are 3 different ones, but they can have different masses, but I'm not able to explain you the mass hierarchy in the electron muon on top. So I put them in singlets, and then you could maybe add Frogger-Nielsen charge or whatever so that you can explain the hierarchy. I'm mainly just interested in the outcome that in an appropriate basis, which I can choose, this is just a diagonal matrix, 3 different entries, and then I'm happy with that. And then we are not looking at this anymore. We are just right away turning to the neutral states. Okay. So now we discussed already why we want to have this in this triplet. Now I'm just deciding that I also want to have the N and the S in the same place. So what happens if I do that? It will turn out that, as you can see here, because of the structure of the matrix here, so you couple a 3C bar with a 3C if you want, that this is actually it's 3 times 3 bar, as you know, from SU3, is invariant. So this one you can write down while not breaking any of the symmetries, which is nice. In the middle, you can do the same because you get the 3 bar times the 3. So also this M&S matrix here, you can write down while not breaking any of the symmetries. So that's my choice. Where's now the symmetry breaking sitting? Guess what? Here in the Majorana mass matrix, because we said that this is a complex three-dimensional representation. So if I write down a 3C bar, which is equivalent to a 3, 3 times 3, if it's a complex irrep, doesn't make 1. So in order to write down something for this mu s, which is non-zero, I need to break the symmetries. And how I should break them, I know, because I want to have this g nu as my residual. So what does this tell me? It tells me what the structure of this mu s should be. And actually I can write it in the following way. I have 3 free parameters, and I have this matrix US, which is omega is given by the choice of the CP symmetry. And here you see you recover the free parameter. Now before what we called theta is now this theta s. This is the only free parameter. Otherwise this is a rotation in one plane. Okay, so this is the amount of free parameters you have. You have the scale for the heavy states, you have the overall recover coupling, you have the mu1, mu2, mu3, you have this theta s here.
So are the hierarchies of these scales completely arbitrary, or because naively I would say that if you wanted to break this, well, if naturalness was a guide, you want at least some of these scales to be close to each other.
I mean, in total sense, it's natural that this mu s is small, because if you send it to 0, you conserve lepton number. Right? Yeah.
But then since you're
this
putting
one is obviously, because it's a Higgs coupling, it's expected to be weak scale, right? So that's not magic.
Sure.
This one here we can debate. Okay.
So that actually was my point, because you're putting N and S in the same groups, same structure.
Yeah.
I would naively expect whatever that scale of breaking is should transmit to N, and then naively whatever scale it gets should be.
Yeah, you can, I mean, as you see, I can write it down without breaking any symmetry in this scenario which I've chosen. So you could be saying this is a free scale, so I just expect it to be larger than the weak scale. Okay?
Right. So ideally,
it could be also Planck scale, but I don't want. If it's Planck scale, I have no pheno to talk about. Okay, then, but in principle, it could be anything. Okay, you see. I mean, that's the point. I can't tell you the hierarchies of the charge leptons. Neither I can tell you the exact scale of this one. So that's not included here. But obviously, you can include it when you think about, as you were saying, you think about how to break the symmetry, at which scale to break the symmetry. Yeah. All right. Good. So what now you can do, you have a few parameters only, as you see, which describe this scenario. And now we can check out how they are matching onto the phenome. The first thing what we can calculate is the light neutrino mass matrix, and it looks like this, which means we know that the light neutrino masses are determined by the mu1, mu2, mu3. So each of them has its own free parameter, which means I can get the neutrino masses to work. I can't tell you whether there should be a preference for normal ordering or inverted ordering or whatever, but I can describe correctly the phenomenology. That's good. And from here, I can also read off lepton mixing, and I can read off that this UMS matrix here is actually exactly this US. If you go one slide back, it's actually turns out to be exactly this US, which means that this theta s here is going to be the free parameter which we have to use in order to adjust well to the measured lepton mixing angles and see whether we can do or not. So then if we look into the sterile states, they're very boring because you're not breaking the symmetry by writing down the main mass term for them. So they turn out to be a pack of 6 states which are nearly degenerate, forming 3 pairs of pseudo-Dirac states, which are, nearly all of them are nearly degenerate. Now, we can go beyond leading order for the light neutrino masses. And so when I wrote down the mass matrix for the light neutrinos, this is obviously an expansion in assuming that μs is much smaller than MNS. So the next leading term, if you want to see it, here it is. Now you know the forms of these matrices, plug them all in, and find that actually this has the same form as the leading term. So we get a little shift, usually this gives a little shift. The masses which we have, it doesn't do anything to the mixing. Then we were talking about this non-unitarity, so that this actually is a would-be PMNS, and that this eta comes in here, and this eta will encode the impact that the stereo states are having on the lepton mixing. So the eta we can calculate here, and this eta has funny properties due to its structure, how it's calculated this way, so that it actually depends only on the 2 matrices which are not breaking the symmetry in any way. We find 2 funny points. Point 1, which is funny, independently of which kind of lepton mixing pattern you want to produce, this eta is always going to be the same. And the phenomenologically funny point, if you want, this eta is flavor diagonal, and even more so, it's flavor universal. So you can easily constrain it. So you go to the paper where there are constraints on these entries of this eta matrix, and you see if you have a flavor diagonal and universal thing, the strongest one comes from the eta mu mu. So what do you constrain? You're actually constraining the combination of M0 and Y0 of this overall Yukawa coupling and of the mass scale, mainly of the mass scale of the heavy states. And for example, as benchmark, take the Y0 to be 0.5, and then you know that your stereo state should be roughly larger than 2.5 TeV. Okay. Now the crucial question is, because I said I do all these symmetries and stuff because I want to have some prediction for the lepton mixing and so forth. So now the question is, these non-unitarity effects, do they actually spoil my predictions? So we look at case 1 again, and we look at what happens to the solar mixing angle, which had this form in terms of this free angle theta. So now here's plotted the difference in percentage between the value which we originally got without the non-unitarity effect and the ones which we get with the non-unitarity effect. Now you see here's a scale which says minus a few percent. You could say, oh, this is big, but then watch out, this is all in this gray region. And the gray region tells you that for Yukawa coupling, which is 0.5, actually your M0 should be larger than more or less 2.4, 2.5 TeV, okay? So what you are seeing here as large, potentially large effect is, sorry, all already excluded because then you would deal with too light. So in principle, you only should look at the white space here, and the white space, sorry, I switched to the next one, but it doesn't matter, it's just another angle. So the white space here tells you what actually are the deviations which you can expect. So well below 1%. So which is for me as a model builder is nice because I say, oh, my predictions are not spoiled by this implementation in the InvestSeesaw. You can do it for the other mixing angle, theta to 3 as well. Looks similar. You can also do it for what is called a sum rule, since you have 3 mixing angles, which depend all on one free parameter on this theta. Obviously, there is an interrelation between these things. And this is what is a sum rule between the solar and the reactor mixing angle. Also this, if you look just at the white space where it's allowed, actually you would see, I mean, it's way sub-percent, cannot be detected, this deviation. You can ask for the Majorana phase. Maybe we are more lucky with the Majorana phase that their deviations are bigger. Sorry, not the case. as long as we're in the white region where it's allowed, it's not. We were asking ourselves also because the Majorana phase has this funny dependence with this sinusoidal dependence on this phi s, which is actually this S, as we said, describes the CP symmetry which I choose, and this N is the index of the group, right? So you can ask yourself, would this be kind of destroyed if I dial up really these non-unitarity effects? And you see, no, it kind of, these things lead only to a damping if you want. The amplitude is lower, but still the periodicity is the same. Nevertheless, should you trust in what you see here in the sense that it's phenomenologically viable? You know, we have taken the Yukawa coupling to be 1, and then the only allowed value of this M0 actually is going to be 5 TeV. And then you end up on the same curve practically, which is this. You see that there's a black dash curve, and below that should be a green straight curve. That's for 5 TeV, and the black dashed is the one which you get if you don't include any of these non-unitarity effects. So, which tells you, again, hypothetically nice to study, but visibly you won't see any deviations. That might be a bit depressing. You can ask, would I have more chances if I would study the other 2 CP phases, which were constrained to be trivial, so sine delta to be 0 and sine beta to be 0 for this case 1. So you can go to case 2 where they're not 0 in general. But sorry, same message. Effects are very small. And lastly, you can ask yourself, okay, do I have more chances if I look at different phenomenology of this kind? I look at now charge lepton flavor violation because it's very well known that if I'm in an inverse seesaw, I usually have quite sizable effects of charge lepton flavor violation. So, long story short, because of that, you might hope, but then you notice that flavor breaking and lepton number breaking is coming from the same source. You also notice that this eta is proportional to the identity matrix. Then you notice that the states which you add, they're actually 3 pseudo-Dirac pairs, which have exactly the same mass, more or less. And this information you all take together, and then you can make an analytic estimates using the well-known formula, which you find, for example, in this works here. And you find out that the typical branching ratio for mu T gamma or something like that is going to be 10 to minus 50. So they are looking exactly standard model-like. And the reasons I've given you on the slide. Because having this as ingredients, you can check that there's no chance of seeing it. So what's the conclusion? The conclusion is option 1 works very well, but it's extremely hard to testify or exclude. Any questions to this?
5 TeV is not reachable.
Yeah, I mean, it's the, yeah, what shall I say? It's my collaborators were more depressed than I was. I mean, I was happy that it was a scenario, if you want to see it positively, where you get the results which you get from the symmetries for the lepton mixing. They are not perturbed strongly by the new physics which you add, this inverse seesaw. But my colleagues there, this French group, they were heavily depressed because there was no way of easily excluding this kind of scenario. So, but yeah, so that's the way it is. You might say that obviously this is due to the fact how we implemented this breaking of the FNCP to G nu for the neutral states. So you can think about what happens if I change this. I'm not forced to do it as I did it before. So now, how much time? 10 minutes? Or I mean, we started a bit later, but
yeah, we can. 10 minutes is okay.
Then do 10 minutes.
When do you have to leave?
I don't know.
Oh, I have time. Okay.
Everyone is free to leave whenever he, she, or wants. But so now the idea is look at what we call option 2. So it's a different thing. You see what's the essential change in it. Let's be a bit quicker. The essential change in it is how these neutral states transform. So now I proclaim, I just tell you that these neutral states should transform as a real representation which is in general unfaithful with respect. So that's not reflecting the entire symmetry structure of this delta 3n square or 6n square, but it's real. So why is this nice that this is real? Because since it's real, I can write down now this mu s term in the limit in which there's no breaking of the flavor or CP symmetry. I can still write down the m and s term because they both transform in the same way, also in the symmetry preserving limit. What now is actually doing the symmetry breaking is this coupling between lepton and lepton doublets and these ends, which we usually would say right-handed neutrinos. Okay, so that's how the story changes. And this changes literally everything, if you want, in particular regarding the cLFVs. So you would have these matrices, you say, oh, boring, boring, because not breaking the symmetry. And then you have the part which breaks the symmetry, this YD. So how do you choose this YD such that it actually preserves the symmetries, this G nu Z2 times CP that you want? So you have to ensure this is the condition telling you that it's not breaking the Z2 because this Z3, so this Z3 and Z3 prime are the generators corresponding to this Z2 in these different reps. And then it also should preserve the CP, and the condition you see here in terms of this axis, which are like the axis which you have seen in the beginning when I was introducing this, so to say, generalized. And now, this, obviously, you can write down what is the most general structure of this YD satisfying. Okay, remembering that even it seems abstract to you, but this Z and the axis, these are matrices, 3x3 matrices, just numbers. So in particular, you can write this, connect this axis to these omegas, which we already seen before. So, and if you do it well, you see the most general structure which you can have is this one, where you might be scared now what is actually free parameter and what not. So these omegas are determined by the CP symmetries, so they are fixed. Then you have a theta L and a theta R, so now we have two angles, so to say, not just one. And you have these Y1, Y2, Y3, these are three Yukawa couplings. So let's collect the free parameters. In addition to this, what we have seen in the YD, so these Ys and the theta L and the theta R, we have these two scales. So we have M0 and mu0. So how do you actually now understand, how do these scales translate into something which is physics? So the M0 is telling me what's roughly the mass scale of this pseudo-Dirac test or of these stereostates as before. So that doesn't change. The mu0 tells me what's the size of the lepton number breaking. This YF, so the three Yukawa couplings here, I use now to adjust. These were like before mu1, mu2, mu3. Now I use this Y1, Y2, Y3 to adjust the three light neutrino masses. For the two angles, now, the theta L is the one which I use in order to fit the lepton mixing angles, or to get close to this and see what kind of predictions I get for the leptonic CP phases. While the theta R is a free parameter which is not directly related to anything in phenomenology. Now you might ask, what is the typical range? I was saying this before, but imagine for these masses of the stereostates, they are roughly going from the electric scale higher. So you want to be more conservative, start at 500 GeV and then usually go to 20 GeV. That's the scale roughly for them. The mu, which is the lepton number breaking, so this source should be always small. Yukawa couplings can be anything, as you know. Here they typically turn out to be this range. Theta L, I fit, so I don't give any range for it. And theta R is a free parameter, so I take all the range which is allowed for one angle. And now I can study for all these different cases which I have, which give me different lepton mixing patterns. I can study the phenomenology, both analytically and numerically. So I jump over the stuff with the impact of the lepton mixing, because this turns out to be just a slight generalization of what we've seen for option 1. So it's not a huge effect. Now, I would focus on the cLFVs, and there are three analytic things which are good to keep in mind, which everything is well known. This is nothing which we kind of invented. So is first of all, at leading order, these things are all proportional to this one entry of the eta matrix squared. And here for the mu conversion, it will be eta e mu. This turns out to be the dominant one. Second thing is, often for trilepton decays and mu conversion, the Z penguin will dominate here. If you just plot the different contributions which you have to these processes. And eventually, which is curious for the conversion rate, it's well known that the conversion rate depends on the nucleus you use. We are going to focus on aluminium because that's the target for the future experiments, COMET and mu2e. There is a point of exact cancellation, which is determined by the type of nucleus you use, which essentially tells you at a certain particular mass of this stereostate, you should see that this rate is going to drop. And we will see this in the next few parts. So these are like kind of analytic guidelines, not to have surprises than what you get. So let me maybe just talk about case one. So for case one, you saw that we had this parameter S, which were telling us the CP symmetry. Actually, it turns out if you look at this eta here, that this S disappears because you can write this matrix U0 or theta, which is relevant for the eta here as separate. You can kind of separate out the dependence on the S, which you understand analytically if you just look at these forms of these matrices, which means it drops out here because we have this combination of the U0 and the U0 dagger here. So
what is omega? Because it looks like it's not discrete, right? Because phi s can take continuous values.
So the omega actually is determined by, so I tell you what the CP symmetry is, then I tell you an X. And this X you can write as omega transpose. So this is the omega. The omega is, so to say, representing your CP symmetry.
I was thinking of it as a permutation group, but it's not. It's not a permutation. Symmetry.
No. But it's still, it's a, in that sense, it's, if you ask, is it discrete or not? But once you fix, so you always have to imagine that you fix the S. You say, I take one CP symmetry, then this phi S is fixed, right? Then this is because then you also can say I fixed the group, then the N is fixed. So that think about this, that this is something which always has numbers in it, okay? There's no free parameter in the sense. And what you can say free, if you want, that's the choice of the symmetry, which is hidden in this phi S, okay? That's the good point about discussing this in a certain class. I'm not forced to take really one symmetry, one N and one S only, but I can do it for all of them at the same time, right?
So the U0 in that sense is not really. So I was naively thinking of omega 3 times R as some rotation matrix that would take R to U0, but that's only true once you fix phi S, then it can just rotate the basis.
I mean, it's if you want this one in a certain limit corresponds to the PMNS matrix. Okay, it smells a bit like what we see in this structure before. It's always this omega times the rotation matrix, right? Here it's not in general that simple, but so I wanted to keep this under the rug. I wanted to focus here on the cLFVs and the fact that actually this S, although you might think it enters and it's relevant, it's not. And we also checked this numerically. So we set it in the following orders to 1. Good.
So it's not relevant for the charge lepton flavor, but it's of course relevant for the.
I mean, it determines what the Majorana phase alpha is. Yeah, you're absolutely right. So, but you can formulate it in a negative way. We can't access S through the cLFVs.
I guess it makes sense because it's
I mean, it's not lepton number. Yeah, exactly.
It's
Lepton number conserving and not violating. Yes. So what do we first? We first say, okay, let's start slowly. We would like to inspect what's the dependence on this theta R. And what do we do for that? We fix the two scales. We have set the S already to 1. If you want, you can set the N to some value. We set it to 26 just for showcase purposes. And then what we do, we keep the theta R free. So you see these different colored lines are for different values of theta R. We also keep the theta L because it's another angle. We keep also this free. So the first thing, what you notice, so the branching ratios you get from mu to gamma can be sizable. And there is indeed some potential to exclude, both for normal and inverted ordering. In some regions, some choices of theta R and some combinations of theta. You can say good. You can look at this for the mu to 3 to get a feeling of who could be more constraining or what. And you see, yeah, mu to 3 in particular, if you reach the phase 2, the mu to 3 experiment turns out to be much more constrained.
Then how much are they correlated? So you said there was set penguin.
I will show you plot later.
Okay.
Give me 5 more minutes and then we are through and I show the plot, okay? The third thing which you unbiasedly can look at, this is mu conversion in aluminium, which should be super strong, and indeed it is very strong. So here, I remind you, I fixed arbitrary some mu0 and m0, so this is might not be, keep in mind there will be the cancellation possibility for the mu conversion. However, what I did here, I added new piece of information. Apart from telling you what the exact values of the theta R is, I tell you also now, you remember the theta L I use in order to get as close as possible to the measured lepton mixing angles. So, and if I want to be at 3 sigma okay with the measured lepton mixing angles, I should be in these very thin colored regions. So, what do you see here? Definitely, what is still allowed as parameter space by mu conversion is highly incompatible with a good fit to the lepton mixing angles. So this tells you either you do one or you do the other, or you put it conversely. Since the lepton mixing angles have been measured, so you should do first this one, and then here you will get signals which are very easily measurable. I mean, if comment on mu to E switch on, they can be easily in the reach of 10 to minus 15 to 10 to minus 13. That's good. But keep in mind, I now sit on one particular point for this scales, which is not true that I know which scales are the right. But this was just to explore, to get a feeling of what happens if I now vary the theta R. So be more ambitious. Now we vary the M0 and the theta R. But we still keep the mu0 fixed in order to get it slowly. And we fix always the theta L such that the lepton mixing angles are fitted well. So now what we want to look at, what's more or less the behavior of with respect to M0 and for different values of theta R. So you see, what can you learn here? You can learn that the mu to gamma actually is nice, but there are some values of the theta R for which you can't exclude anything. Not even for this mu0 being 1 keV. And even small masses of the M0, ridiculously small, like 150 GeV. This changes drastically if you look at the mu to 3. So there you would say, if I want to survive, in particular phase 2, I should be only sitting at very small values, or here for inverted ordering, I wouldn't really kind of manage it for this fixed value of the mu0, okay? So now let's come to
Can I ask one question now?
Sure.
So since it's counterintuitive, so M0 is the mass scale of the heavy stellar neutrinos. So increasing the mass scale, it's exactly, it looks
at a certain point this breaks down. You're absolutely right. It's not, I mean, take this with a grain of salt. Don't overdo it. So don't look at probably here, there's a certain cut where you should not look at. But it's true that it's kind of, at first it has a raising behavior.
So it's compensated by the Yukawa couplings?
Yeah, it's going to be compensated by other effects. But not overdo it. So not going to, I mean, we, for just showcase purpose, we go to 50.
Okay.
It's not meant to be that large.
The Yukawa is also quite a big hierarchy, because you said at some point the Yukawa started 10 to the minus 5 to
Yeah, this is if I look at the entire range. So, you know, we do the scan, and in the end, we look at the entire range. What's the smallest UCAVA what we ever get, and what's the biggest what we ever get? Yeah, just to give you a feeling of what it's the typical size. So, for example, for the UCAVA, we never ran into perturbability limit problems. That's the
It's
point.
1.2.
What we wanted to know, right? We also didn't want to get extremely tiny. We said maybe what's a good lower bound would be like the UCAVA of the electron. So we want to be not too extreme. Right? Okay, now here comes the thing with the conversion and the cancellation. So if you sit around here, you're always good with mu conversion simply because you're sitting at the cancellation. That's the fixed number which I was telling you, which is roughly 6.5 TeV. You always have this is independent of the case, this is independent of the choice of theta or whatever. You see, it's always the same. They go to 0 because that's only determined by the local change. But you see, obviously, this is would be far away from what you could claim to be like more preferred by the Newton 3. So you see that there's a discrepancy. But this was like, if you want, only like some sort of first exploration. Now we do the scan. So we do the scan, and this is the result of the scan, a panel of like our three primary keys we looked at, and this all plotted versus M0, mu0, and theta. So first of all, if I want to keep it brief, only look at the points which are colored according to this color bar here. The rest is somehow excluded, okay? So ignore the gray points, the orange stuff, and the red stuff. Just look at the other colors. And remember that this is like an intermediate. We wanted to have some figure of merit, which we kind of can tag the data points, and we use the average value of the UCAVA. That's the tag which we use. And now let's come to some observation. What we see, we find viable points for mu0 being at least 2 keV. So the one which we used before as benchmark value actually was always excluded. Then you notice some funny thing, or you might be a bit curious about the behavior of this theta r with respect to theta r, because you see that this actually has a trigonometric functional structure. And you see roughly that it's enhanced if the cosine of 2 theta r is small. And if this one is large, your branching ratios get suppressed. So now the big question is, where does this come from? This comes from because in this eta, the UCAVA couplings appear, and the UCAVA couplings actually have a behavior on this parameter as well. And if this small one gets small here, I need a larger UCAVA coupling to still get the same mass of the light neutrinos. So it's kind of, Janis knows this effect, because we write essentially, you will find that at least one of the masses of the light neutrinos goes like a UCAVA couplings times the cosine of 2 theta r. Okay, if you drive this cosine of 2 theta r to 0, you have to go up with the UCAVA coupling in order to manage to get the light neutrino mass spectrum, normally ordered, and the lightest neutrino mass 0.03 electron, which explains you why you get these peaks. And if this grows large, the UCAVA coupling, also your branching ratios and conversion rate goes large, and you exclude. And if this one is larger here, this cosine of 2 theta r, you have a suppression, so to say, because you can commit yourself to have smaller. Okay, and then you can also wonder now what's the strongest constraint here actually. And then we would say, look at that. We went through all the data points and we saw we reached the bound which comes from comment, which is the strongest prospective bound for the mu conversion. We also we have regions where the phase 2 bound of the mu3e experiment is reached. So these two bounds, you can say, are effective in the sense they're really cutting parts of the parameter space, while, which you don't see here, the maximum which we can reach via the data point for mu3e gamma is going to be 2 orders of magnitude below what the Mach2 prospective limit, which is 6 × 10 to minus 14, gives you. So bad news for them, better news for me if you want. And Michael, you were asking for the comparison between them. This one you wanted to see, right? Okay. Here you can see, okay, on a log-log plot, more or less everything looks like a line. But you get an impression of that. It's true that certainly there is a good portion is dominated by just this eta e mu square, because then you have this direct proportionality. And then you see obviously the spread. Where's the spread of these things usually coming from? This is from different contributions which you have. Where you have for mu to gamma, usually just one contribution. You have for mu to 3e and mu conversion, you have more than one contribution. So also Z paying run in boxes, and this explains the spread. If you want in this confrontation judge on which experiment is the best, you would say, yeah, mu to e gamma is nice to have, but it's not cutting much out, because you see, I was telling you the gray, forget about the gray points, the orange points, they're cutting this a bit, but also it's not very strong. You would say rather you go from mu to 3e, and particularly in the second phase, because this brings you down here. So while you see in direct comparison, the mu conversion rate is smaller. So the gray points, they mean it's already currently excluded by these eta constraints, while the orange points telling you that there's one of the new bounds, the prospective bounds on the tree, going to be violated. So you have to see how much one of these processes is responsible for cutting out some of these orange points. And you see most of the orange points are cut out actually by unit conversion. So this is the one we like most. But still, even if that's effective and also in combination with Newton 3, the model is not going to be, all the scenarios are not going to be dead. So you still have some minor problems. And I jump over case 2. I just do some very quick thing, because we like to see maybe what about if you're not sitting in the mu e channel, what could something interesting be happening for Claudia case? Very brief. This is the result. Nope. Is the answer. Because if you just look at the scales here and at the points which are colored according to this color bar, you see usually you reach 10 to minus 15, 10 to minus 16, 10 to minus 14 with a lot of goodwill, very much below anything that you could say. Okay, I just stop. I don't think I need to read out the conclusions or the summary. Just thank you for your attendance.
Yeah. Thank you very much. You had already a lot of discussion during the talk, but I think there's still space for 2-3 questions.
Zoom maybe.
Zoom. Yeah, if nothing yet, but maybe let's speak up. Janis?
Question about these plots and the correlations. How well, I mean, maybe two questions in one, in the sense, like, first of all, like, what's in a sense the priority? Like, does the density means something like that would be, I guess, the typical thing that you expect? And then what's the bottom of the plot? Can you reach exactly 0? I mean, is it something where I can?
So you are asking, okay, the density of the plots, obviously, the density of these clouds is determined by the way we did the scan. So the scan is always done in a certain way. You might have certain prejudices of where you would like to have a higher density. For example, we had a certain prejudice of that. For M0 being between 1 and 5 TeV, we have most of the points. For example, that's just so in that sense. Don't take the density of the points necessary as fully representative. If you ask for a possibility of having strong suppression of one or the other branching ratio or conversion rate, that's what you were asking, can it go to 0? Obviously, if you sit right in this cancellation, then you would have to sit on a very particular value of the M0, then you can always avoid the conversion. That's the one. If you look at the other ones, you see that we have some points which are raining down here. You can also get small rates for the other two. if you want. But you see, it's rather rare. I think you can take it as a certain indication. Don't make a percentage out of it, but still take it as a certain indication that it's not likely to be, that they're very much suppressed. So the bulk will be.
So this bottom is kind of I mean, the bottom of the plot from nuclear gamma and stuff like that. It's like kind of a funnel which is difficult to reach, but if you kind of tune certain parameters, like can go to very.
If you ask me in detail for what are the numbers for these points, I would not be able to tell you from the top of my head, but I can show you a counter example. If you go to the other case, you would find that they're actually, the other case has lower limits.
Okay, yeah.
But this is due to, but this you can trace if you want to do a detailed study. We haven't done that in the experiment. You can detail study, then there must be some sort of either possibility of cancellation in these eta elements or not. At least depends on this case. Yeah. Okay.
So does n equal to 26, is it special? Because you have a heat.
No.
That's the size of the gauge group, right?
That's the size of the group.
That's the size of the group, and you want. If that's the size of the group, you have some particles, some number of particles charged under that.
No, I mean just to say, why did I take n equals 26? First of all, we took it in the other study for the option 1. We also took it, so we wanted to take the same example. Second of all, when we started with that, we were not sure whether this depended somehow on the s. And I told you the s is varying between 0 and n minus 1. So if I want to be cautious, I take a bigger n because I want to have variations in the s in order to have a chance to study this phenomenology, okay? That's corresponding to different types of CP symmetries.
So, but are there particles charged under that? Are there? So naively, if you, at least in continuous groups or something, if you have a group of a certain size, you have a certain number of particles in the fundamental of that group, at least.
I mean, I always have at least a pack of these, and I mean, I always have the left-hand and left-hand doublets, which are in the fundamental, if you want. They are in the faithful Arab of this group, but this is always three-dimensional. So free your mind of this fact that if the group gets bigger, the representations get bigger. That's not true in discrete symmetries.
I see. Okay, that's true. Okay, right. That is true. Yeah. Sorry.
Yeah. So that. Sorry for that.
Okay. No, so that's. Yeah.
You can't make anything out of it. If you don't like the 26, you can replace it with, I don't know, whatever you might like, a smaller. And not so. I mean, just do it. Take a smaller number, which is even. The only thing.
Yeah, it's a discrete.
Yeah.
Okay, good. So I would say we finish the official part. I have actually some more questions, but I see that other people have to leave. So yeah, thanks a lot, Claudia.
Thanks to you.